Okay, so last class today. I want to mention that the course will continue same time, same place next spring, and next spring will be all quantum all the time. This semester it's been mostly classical, and I think worked out that we're kind of ending in a very nice place because we're going to be talking today about the laws of black hole mechanics, which were, I view as kind of the culmination of, they were completed in the early 70s, and they were kind of the culmination of half a century of thinking about black holes. People really began to understand what they are and how they behave, and it's very beautiful the way these classical laws of black hole mechanics, as we'll see today, have the quantum begging to be in them. Somehow the classical theory mysteriously already knows about quantum mechanics. Okay. So let me just from last time, well, not last time, that was Peter, but the time before, talking about Kerr. Maybe I'll write the Kerr metric now, write it out now, and save it, which I guess means I want to use this board. So it's the line element. So we define delta, which for Kerr is equal to r squared minus 2mr plus a squared. And we also define rho squared equals r squared plus a squared cosine squared theta. So we have ds squared is minus delta over rho squared. And there are many different ways of writing it. I'm going to use one of the shorter ones now because I'm getting lazy. dt minus I sine squared theta d phi all squared plus sine squared theta over rho squared r squared plus a squared dt minus d phi minus a dt all squared plus r squared over delta dr squared plus rho squared d theta squared. And so this is the Kerr metric. And in fact, we saw that the Reissner-Nordstrom metric could also be written in this form, but with instead of this plus a squared, there is a plus q squared. And the surprising thing is that, in fact, I was going to do this a little later, but I think I'll just do it right now. There is, in fact, a 3-parameter family of axisymmetric metrics called the Kerr-Newman family, which represent a charged spinning black hole. And all you have to do to get that, I don't think anybody really understands why it's so simple, but all you have to do is add plus q squared here. And that gives you the full exact solution of the Einstein-Maxwell equations. And of course, you have to also specify what the Maxwell field is. So that would be A equals minus Q over rho squared dt minus A sine squared theta d phi. So this is, in fact, the full Kerr-Newman black hole solutions, which can be thought of course, as before, we have this parameter A, which is the angular momentum divided by the mass. And Kerr-Newman has three parameters, M, J, and Q. And again, it's surprising. It's a lot of work to show that this solves the Einstein-Maxwell equation. And it's very surprising that you can write a solution in closed form. It could have happened that we needed numerics to find this. Now, astrophysically, we're not so interested in Kerr-Newman. That's why you always hear Kerr, because if there was net charge on a black hole, there's always ions and electrons floating around, and it would preferentially attract the opposite charge, and it would be expected astrophysically to lose its charge in a rather short period of time. So all the astrophysical discussions that we've seen, for example, Shep's presentation about the Event Horizon Telescope, they're always talking about just the Kerr, not the Kerr-Newman. But for the purposes of just considering theoretical properties of black hole, as we'll see, it's very interesting to see what the additional effect of the charge is. Now, last time, you learned that some qualitatively new features of the Kerr black hole. It has a horizon at r equals r plus, but then there's a second surface, the so-called stationary limit surface, which is, let me use a different color. Looks kind of like this. And this is r equals rs plus, which is equal to m plus or minus the square root of m squared minus a squared cosine squared theta. And what happens inside the stationary, so if you're out here, I'm just reviewing what you discussed last time, or 2 times ago. If you're out here, or if there's a black hole somewhere in the middle, or Sagittarius A star, let's say it's spinning around, probably is spinning around, there's no reason for it not to be spinning. It is trying a little bit to drag us with it around, but it's not very hard to resist. It doesn't take very much force to resist it. We can stay in the same place. But as you get closer and closer to this stationary limit surface, you have to sort of walk in the opposite direction faster and faster to stay at the same fixed angle. And inside this surface is a region called the ergosphere, where you must orbit around, you must obey the black hole, and you must go in orbits around you must orbit around it. So this is a region of space-time which is very different from the familiar region in the room. And of course, just as of this month, we've probably seen this region. It's likely that some of that light in the EHT image that we're seeing pass through this region. So it's not invisible to us like the inside of the horizon. So maybe it's not as weird as the inside of the horizon where you're commanded to enter the singularity, but you do have to do some weird things once you're in the ergosphere. Okay, now one of the so at the EHT they probably saw light that passed through the ergosphere. You can go in, you can go out. Also, if you can go in and go out, you can get rich while you're in there. You can get a lot of energy, and so that's what the first thing we're going to talk about is the sort of Penrose Christodoulou energy extraction. So you can sort of pull a piece of the black holes. You can't do this with Schwarzschild, but the ergosphere is the region in which, another way you could define it, it's the region in which you are able to mine some energy from the black hole. And indeed, M87, indeed, astrophysically, this is a really important source of energy, and it's believed to be the primary source for most highly visible highly visible events in the sky. So for example, I think it's true that I think I read this in one of the recent papers. I didn't look it up again, but I think that the jet from M87 is so big that they saw it in 1918. They did, and they didn't know what it was, but it's a huge, giant thing out in the sky. M87 is, bigger than the solar system, and then it's got this jet, which is, I don't know, many parsecs, huge amount of energy of the stuff just spewing out into space. And so the first question is, where could all that energy come from? You can't get it by, burning some kind of fuel, or it's just too much energy. And the only place that could supply, that's capable of supplying that kind of power, is a black hole, which is one of the many reasons that black holes are so interesting. They're the power engines of the sky, and indeed, that is the best reason that we have to believe that M87 is spinning, and probably rapidly, because when it slows down, this ergosphere gets thinner and thinner, hard to get the energy out. So to have a really robust jet like that, you need a good, healthy ergosphere, and so that's why the odds are the betting odds. They haven't measured the spin yet, but the betting odds are that it is pretty big. So notice that if we take theta equals pi over 2, which is on the equator, then this is just square root of m squared minus a squared. If it's spinning at its maximal allowed value, which is a equals to m, so this term would be 0. Sorry, I don't have to say anything about the spin. This term is 0 at theta equals pi over 2. So on the equator, the edge of the ergosphere is 2m, so it's exactly where the horizon would be in Schwarzschild. But if you go up to the pole, in fact, that shrinks down, and cosine theta is 1, and this just becomes r plus. So the ergosphere touches the horizon up at the pole. Okay, so so let me now talk about the energy extraction process, and draw the picture a little bigger. So what we want to do is go into, let's say we go into, we have a rocket, which is, and we've run out of fuel. So this actually happened in the movie Interstellar. So I'll describe what happened there. And by the way, I think when I watched the movie Interstellar, which was written by Kip Thorne, there must have been 10 million people. I don't know how many people watch a movie like that. But there can't have been more than several dozen people who understood what they were saying when they explained how they had to throw Matthew McConaughey out of the rocket ship. And I'm like, did Kip write that line for us? You know. So anyway, so that's what we're about to understand. You're now about to understand the secret of Interstellar. So they've run out of fuel. So they're on an inertial trajectory, and they need enough acceleration to get. I think they're going back to Earth or somewhere else. Okay, so they need to escape from the black hole, and they want to go out with more energy. And so what they do, so the black hole is spinning like this. So what they do is, let me be a little more precise about that. Let me say it's spinning this way. So what they do, so the rocket ship comes in, and then they throw Matthew McConaughey they throw him into the black hole, and then they go out like this. And they want to go out with more energy than they came in with. And it's very important here that I've drawn it, that they're throwing him, as we'll see in a minute. This is a precision drawing here. They're throwing him against with angular momentum opposite to that of the black hole. So they're spinning down. They're spinning down the black hole. If they tried to throw it the other way, then they'd be in trouble. In fact, if they did too much the other way, they would never be able to escape the ergosphere, as we'll see in a moment. So they had to know how to aim. And they did, and they explained it as they were doing it. Okay, so what do we know about this process? Well, so here we have a form momentum, P mu initial, and here we have P mu final, and here we have, so we should really think of these, sorry, it's not flat Minkowski space, so we should think of in some inertial frame, P mu initial, P mu final, and P mu Matthew McConaughey, and those obey P mu initial equals P mu final plus P mu Matthew McConaughey. That's just at this point here. Okay, we can add up the three tangent vectors at the point, and this has to be obeyed at that point. Of course, this is a geodesic. tangent vector will change around. It doesn't make any sense to have identities among vectors at different points in a manifold. So this is just a conservation law that tells you something about this process at the point. However, on a geodesic, whenever you have a killing vector, so for example, let's let k sub t equals d by dt be the killing vector associated with time translations. So we get a conserved quantity, the energy, which is I guess minus k mu p mu, which is conserved along any geodesic, as we discussed before. So at any point along this, that is, at any point along any of these three geodesics, we can evaluate, we can take the tangent vector of the geodesic, say we normalize that to 1, we multiply it by the mass, that gives us the form momentum along the geodesic. We contract that with any of the killing vectors at our disposal, which in this case are d by dt and d by dy, and we get a constant along the trajectory. So since these things are all equal at the point, we conclude that E initial is equal to E final plus E Matthew McConaughey. And okay. So what we want is for E final to be greater than E initial. And that's possible only if E Matthew McConaughey is 0. And at first sight, that seems impossible because P mu, whether you're in the ergosphere or not, the tangent vector of a geodesic always lies in the future light cone. So you take a point anywhere in a manifold, the future light cone, have a geodesic running through that point, the tangent vector to the geodesic. So we could write P mu equals mu mu. So the normalized tangent vector, well, whether or not it's normalized, it always lies in the future light cone. Yes? For time-like geodesics, yes. Which the rocket and Matthew McConaughey must always move along. Right. So, yeah, thank you. So, so why can this be negative? Because usually you think ddt is a future-directed vector, and so two future-directed vectors, their inner product will always be negative, giving a positive energy. But the reason is that, in fact, d by dt becomes space-like inside the ergosphere, as you can see if you work out this equation here. That's a way of defining the ergosphere. Okay, so therefore, you must, if you can get P Matthew McConaughey to be greater than 0, sorry, if you can get the energy to be negative, then you'll have succeeded in mining some energy from the black hole. Okay, so if he falls in the black hole, then delta E black hole is equal to E Matthew McConaughey. And also we could have the same discussion about the angular momentum. Just replace, though that's less obvious, that there's no restrictions on the sign of that inside or outside the ergosphere. But we also get a conservation law for the angular momentum by using the killing vector d by d phi rather than d by dt. And so we also get that the change in the angular momentum of the black hole is equal to the angular momentum of Matthew McConaughey. So when Matthew McConaughey, because the total energy and angular momentum are conserved, when he falls into the black hole, the mass and angular momentum of the black hole must change in the way dictated by overall energy and angular momentum conservation. Okay, but now there's an important constraint on how the change in the mass, it turns out there's an inequality relating the change in the mass of the black hole in this process with the change in the angular momentum of the black hole. So, and this was really first noticed by Penrose and Christodoulou. And part of the thing that people were worried about here is, okay, why can't I, take energy out of the black hole? So there's this cosmic censorship conjecture by Penrose, which states that in any physical process, conjectures that in any physical process, one will never produce a naked singularity. Now, if we had a Kerr black hole, and we were able to just remove energy from it, we could remove enough energy so that A was greater than 1. And if you look at the solution with, reduce the mass while keeping the angular momentum fixed, and if you look at the solution with A greater than 1, the R plus becomes complex, there's no horizon, and it's just a naked singularity. So if you found a mechanism of extracting energy out of a black hole without extracting any angular momentum, you could violate the cosmic censorship conjecture. Now, a priori, that could have happened. At that time, when people were thinking about this, people were really worried about whether the cosmic censorship was true or not. 50 years later, people are pretty convinced it must be true just by 50 years of failure to produce a good counterexample. It's still not a proven theorem, but one is not expecting to find ways to violate it. But anyway, so this looked like, at first, like a way that you could violate the cosmic censorship conjecture. And so they tried to, but not quite, not so fast, because it might not be possible to extract energy without also extracting angular momentum. So people were trying to save cosmic censorship. They succeeded in that. But at the same time, they came up with this interesting way of describing a black hole in terms of the laws of black hole mechanics. So let me go through the argument that you can't, produce a naked singularity. And it involves use of what's called the null generator of the horizon, which is given by chi. It's a vector field, dt, plus, so it's a vector field on the Kerr spacetime, which is a linear combination of, this is constant, which I'm going to tell you in a minute, a linear combination of d by dt and d by d phi. So of course, it's also a Killing vector field, because it's a linear combination of two Killing vector fields. And this constant is determined by the requirement that chi be null on the horizon. So in Schwarzschild, you just take chi is equal to d by dt, and d by dt is null on the horizon. But that's not true in Kerr, as one can easily check. But there is another co-rotating killing vector field, which is null on the horizon, and it's called the null generator of the horizon. And it's null on the horizon, but if we compute its norm, chi squared, which is equal to GTT plus 2GT phi omega horizon plus G phi phi omega horizon squared, in general, that's some function of r and theta. Does it depend on theta? I'm not sure. Maybe it did. Okay, it certainly could depend on theta a priori. And omega horizon is taken by evaluating these found by evaluating these coefficients at r equals r plus and choosing omega horizon so that this vanishes. And what one finds is omega horizon is equal to, and I'm going to give two expressions for it. One expression is just a squared over r plus squared plus a squared. Now, so the parameters of a Kerr black hole, we're setting Q to 0 now, are m and j. But just to be clear about this, A is determined by j over m. R plus is m plus this, so those are not independent parameters, but for some problems, it becomes easier to write it in terms of A and R plus. Sometimes it's easier to write it in terms of J and M. So you just have to get used to going back and forth between these different things. So in here, in this kind of discussion, it's nice to talk about M and J because they're the things that we naturally think about changing when we throw. They're the conserved quantities along the geodesics that we naturally think about changing when we throw something into the black hole. Okay, so omega horizon is equal to that, but we can also write it as a somewhat longer expression, J over 2m times m squared plus the square root of m to the fourth minus j squared. Okay. Any questions so far? All right. So now, here's the key observation. When Matthew McConaughey crosses the event horizon, he will be moving on a future-directed trajectory in the forward light cone. Chi is a future-directed null vector. Therefore, chi mu, p mu, Matthew McConaughey, at the horizon, not anywhere else, but at the horizon must be negative. So that says that minus E Matthew McConaughey plus omega horizon J Matthew McConaughey is less than 0. So this is an incredibly simple two lines, and it's a kind of argument that gets used over and over again, and it's very powerful. So if you are in this spaceship and you're trying to throw stuff in the black hole, you know, it's rotating around, it's a moving, you know, maybe a little hard to do, but you know that you will fail if you don't arrange for this inequality to be obeyed. And of course, there's another, if you're throwing something out of your ship and you want to get out of the ergosphere, then you know that your energy, what you're throwing out of your ship better have positive energy. So there are, on your ship, if you can measure the energy and the angular momentum of whatever you're throwing out, you can already determine whether it can go into the black hole or whether it can escape out to infinity. Okay, so that says that minus delta E black hole, or which I could write as delta M black hole, same thing, plus omega horizon delta J black hole is less than 0. Okay, so that means that I can't, in general, so if I try to extract energy, if I set this to 0, if I try to extract some energy by throwing something with no angular momentum, then the change in the mass of the black hole will always be positive, and therefore I will have failed in extracting some energy. And so this is going to conspire to keep us from violating cosmic censorship. So the next thing that happened was Christodoulou noticed something called, defined something called his irreducible mass. So he just looked at these equations, and he was a graduate student when he did this. He went on to do great things in mathematical general relativity, but this was his first work. So he defined irreducible mass by m squared plus the square root of m to the 4th minus j squared. Just pulled this out of a hat. And so let me rewrite this as delta m black hole minus omega h delta j black hole is greater than 0. And let me drop the BH subscript. That's all we're going to be talking about now, is how the mass and the angular momentum of the black hole change. And so if we take the change in this process of this m squared irreducible, well, it becomes, from the first term, we get m delta m. And the second term, we get two things. And so we can write it, so we get plus m cubed from varying this, delta m minus j delta j, all over square root of m to the 4 minus j squared. There's a half there, a half j delta j, which we can write as, if we factor some things out, we can write it as j over 2 square root m to the 4th minus j squared delta m over omega horizon minus delta j. Okay, so you pull this out of a hat, you compute its variation under this process, you find it's proportional to this, and that is therefore greater than or equal to 0. This is actually, I guess, strictly speaking, well, I think it's, yeah, so there's a subtle question of whether you can saturate this inequality, and I don't want to get into that whole discussion, but I think you can't. Yeah, okay, I guess it goes back to here. If this is not null, this can't be strictly 0. It must be less than 0. Okay, so, but that begs the question a little bit, because we might consider a more general situation where we shoot a light ray in and try to violate cosmic censorship. Okay. So that's greater than or equal to 0. And therefore, there's something, this so-called irreducible mass, which no matter what you throw into the black hole, no matter how you come out, it may be that the spin went up or down. It may be that the mass went up or down. But the irreducible mass is something which is always increasing. So that is strange, and that's going to come up a lot. All of a sudden, we have a quantity in general relativity which is always increasing. Rather strange thing in a theory in which the equations of motion are time symmetric. And how could it happen that you have something which is time symmetric, and all of a sudden it has to increase in one direction? Well, it's because of cosmic censorship, that we don't allow singularities in the past. And if we allowed singularities in the past, we could have things that, if we allowed more, it's because of the asymmetric way that we imposed our initial conditions. And so we don't think about things with singularities in the past, but we talk about formational black holes where you get singularities in the future. So there's a fundamental asymmetry in the class of solutions that we consider. And that asymmetry leads to the fact that there can be things which increase to the future. Now, something very similar happened 150 years earlier with Boltzmann, where he started with the theory of molecules and he applied statistical reasoning and found that there was something that only increased in one direction, namely the entropy. And well, that really confused people. This really confused people. They turn out to be the same confusion. But that's something we still don't fully understand. But anyway, turns out that if we compute the area of the event horizon, which is r, the integral over r equals r plus, at r equals r plus, just square root of g theta theta, g phi phi. I think this was a homework problem. D theta d phi. This becomes 4 pi r plus squared plus a squared, which works out to be, if you work this out, it works out to be just 16 pi times the irreducible mass squared. So Christodoulou had found that the thing that always increases is just the area of the black hole in these infinitesimal processes. Now, there's another argument which I almost surely won't, well, yeah, I don't think I'm going to get to. But there's something called the area theorem, which is much more general, which was various versions of it were proved by Hawking and Penrose, and that if you have an event horizon in a so here we're not exactly looking. This discussion is not exactly about solutions, exact solutions of the Einstein matter equations. We're doing a kind of perturbative argument where we start with a black hole and we put a little test particle and compute the back reaction to first order. The kind of argument that should work. But there's a more general argument, which I think gives less intuitive insight and uses cosmic censorship, that for any, so in a general time complicated gravitational collapse scenario, at late times you'll have a black hole which will have a event horizon which will be at some fixed radius, and then eventually you'll cross the collapsing shell of matter, and eventually it'll end in some caustic. Doesn't have to be during the formation process. It won't be spherically symmetric, some general space-time. And even in that very general situation, it's been proven, assuming cosmic censorship, that the area will always increases. You see, this argument, now that I think of it, and I just realized this point as I was saying it, this argument doesn't really, what's nice about this argument is it doesn't assume cosmic censorship. It doesn't, neither does it prove cosmic censorship, but it shows that with this kind of process, you can't violate cosmic censorship. And it also gives you an idea of why cosmic censorship isn't being violated, because a particle that would give enough angular momentum to the black hole to send it into a naked singularity gets repelled away from the black hole before it can cross the event horizon. Okay, but it is a very general statement that which is called the first law of black hole mechanics. Sorry, the second law of black hole mechanics, that in any process involving a black hole, the change in the area is greater than equal to 0. And moreover, this is called the second law of black hole mechanics, but we also have a formula from here which we can recast into a form of the first law of black hole mechanics. With rewriting this, we can get a formula for delta M in terms of the change in the area, and it works out to be the square root of m to the fourth minus j squared over 16 pi m squared plus the square root of m to the fourth minus j squared times the change in the area plus omega horizon delta j. So this is known as, I should have written them the other way, but this is known as the second law of black hole mechanics. You know what? I think I'm going to write it down here. So I have delta A greater than or equal to 0. This is the second law of black hole mechanics. And this is the first law of of black hole mechanics. Okay, so the first law of black hole mechanics is really saying that the area of the black hole is simply saying that the area of the black hole is a function of the mass and the angular momentum, so that if you know the change in those two, you can figure out what the change in the area is. It's not an independent quantity. Okay. Now I'm going to move on to discuss any questions about that. Yes?
Yeah, I have a question about the cosmic censorship. So I'm a little bit confused about the fact that the Lagrangian, as you say, has time reversal symmetry.
Yes.
But any solution of the Lagrangian obeys cosmic censorship. And therefore we assume it. Or like, is that the logic?
So good question. It's a very funny thing. So the statement is this. This is a Penrose diagram for Minkowski space. And the statement is that if we start with a smooth space-like slice without a singularity on it, in general, it's known that if we evolve to the future, we might make a black hole. But the cosmic censorship conjecture, I guess I was going to say something about this later on, but I'll say it now, says that you might make a singularity, but there'll still be a null infinity, which is geodesically complete. That is, it doesn't end at a finite retarded time. And moreover, this singularity is invisible to any observer at null infinity. So in other words, as we discussed before, the causal past of null infinity, the complement of the causal past of null infinity is the black hole. So that's this region here, the region you can't see from infinity. And cosmic censorship is, yes, singularities may sometime occur, but they're always hidden inside of an event horizon. So, I mean, you could take so because it's phrased in a time asymmetric way, it doesn't violate anything. The conjecture doesn't violate the statement that if you have a solution of the equations of motion, that its time reverse is also a solution. It's just, so this could have arisen from smooth initial data, right? We believe all the way back at past null infinity. So we could take, time reversal invariance tells us that we could have this, and but we throw this out by hand. We don't allow things that don't evolve from smooth initial data. We put the asymmetry in hand, and it's very much like what we do in statistical mechanics, because in statistical mechanics, you could start with all your molecules at even grids on, some even array on one side of the box, and the entropy would be the entropy would be very small, and then, it would quickly thermalize and occupy a typical configuration with all the, and now and the entropy will always increase. And that seems like it's violating the reversibility of, the microscopic dynamics of scattering molecules, because the solution where you go from the very complicated configuration to all the molecules pinned on one ball of wax is also a solution. But if this makes you feel a little uncomfortable, you're not alone. And indeed, people had a really hard time with what Boltzmann said, and they're still sort of arguing about it now. What is exactly the mathematically precise way to phrase this? And there are still things we don't understand it. And there's also a discussion about in what sense is cosmic censorship really true? Is it always true? There seem to be some counterexamples in higher dimension. So there's clearly some truth in these statements, but what the precise statements are, and even more interesting, the fact, which now seems rather evident, that they're really the same statements in a quantum world. They're dual statements. The area theorem and the second law and the first law of black hole mechanics. The area theorem and the first law of thermodynamics, second law of thermodynamics. So that's something we understand even less. Yeah.
So my impression was that the whole idea for why the solution to the apparent quote unquote paradox of entropy increasing is that we're considering that we're only considering part of the system, right? There's heat coming off, and if we kept track of all that stuff, we'd be able to reconstruct it, right? This has a different sort of fundamental breaking of time symmetry than that. Is the idea
Well, your first statement is not a universally accepted. So first of all, there are 3 or 4 different definitions of entropy. And how you precisely state the second law depends on which definition of entropy you're using, and certainly in some cases it would be applied to a closed system. Yeah. This room is going to be messier now than it was when you came in. Well, I guess wait, that's not a good example. People were coming in and going out. But if you go home and stay in your apartment and lock the door and don't go out, the entropy is going to have increased after a week.
Is the idea of cosmic censorship that if I could write down a Lagrangian for a physical universe, and I specify on some nice slice everything that's going on with all the different matter fields and all that stuff, that if I backtrack that slice, I shouldn't run into singularities?
Well, first of all, in the first instance, it's a statement just about the vacuum Einstein equations. Then we could try to ask whether it included matter, whether you can include matter or not. But no, it's not that statement at all, because this would be a solution. This initial data would well, I just got it by time reversing this. And so if I ran it backwards, I would get a singularity. But the time reverse of that is not a violation of cosmic censorship, because this surface becomes an event horizon. So the singularity is behind an event horizon. So it's not that you wouldn't see a singularity at all. It's that if you do see a singularity, it's one whose time reverse is behind an event horizon. Okay. Surface gravity. So we talked about the surface gravity of Reisner-Nordstrom. So the idea of the surface gravity, just to remind you, is you take a mass, you hang it on a rope that doesn't stretch, and you ask what force you have to apply here to keep it stationary just above the horizon. Then you take the limit of that force as the thing approaches the horizon, and then the surface gravity. So it's a measurable thing. It refers to some inertial frame at infinity. It would be the force over the mass. And we found we could write that in terms of the Killing vector field, which generates the horizon. So those Killing vector fields, maybe we didn't use those words, but they're null on the horizon. So we would use the word that they generate the horizon. That is, if you take a cross section at a fixed moment in time of the horizon, and then you take the action on that cross section with the Killing vector field, it will give you the whole horizon. So it's minus a half. We can write it as dA. Let me call the Killing vector field VB, dA VB. And now we can, so for Kerr, you can't quite define it in this physical way because, you know, this point will be going around it's very rapidly. And if you want to, there's something called the, what's it called? The speed of light surface. If you want to co-rotate with even in non-relativistic, you know, if you're trying to, if the merry-go-round running around and you're trying to run with the same angular velocity, you get too far away, at some point you have to be going faster than the speed of light. So you can't really hang from infinity an object that is close to the event horizon. But still we can use this definition where we just take V to be the null generator of the horizon, and that gives us a geometric quantity, an invariant geometric quantity that we can associate with the horizon of any black hole, even a spinning one. And for Kerr, where's my eraser? Oh. For Kerr, this is equal to r plus minus r minus over 2 r plus squared plus a squared. And we can also write that as square root of m to the 4th minus j squared over 2m m squared plus the square root of m to the 4th minus j squared. And so in terms of this quantity, we see that we can, that this is closely related to this. So we can write this as delta m. Well, let me just do this. So we can write this as kappa over 8 pi plus omega horizon delta j. And now let me add one more thing here, which is, so far we've just talking about Kerr, but for Kerr-Newman, what happens is, so everything we said has a generalization of Kerr-Newman. First of all, it's still true that the area is a function of J, M, and now Q. So we would expect a relationship of this form. And moreover, the surface gravity for Kerr-Newman is still of this form, but now with R plus and R minus being given by the inner and outer horizons for Kerr-Newman, which are just the roots of that delta. And delta m, so what enters in here, you get another term, as you must, involving delta q, and it's just phi delta q, where phi is A0, the electrostatic potential. So the Maxwell theory, so there's a potential at the horizon, the electrostatic potential at the horizon. So these things are beginning to look more and more. It's looking more and more suspicious. These things are beginning to look more and more like the laws of thermodynamics. But let's take a 5-minute break, and I'll continue with that. Oh, hi. Bill, and what was your? Yeah. Okay, so let me now, we're going to come back in just a minute or two to these, the law of black hole, these laws of black hole mechanics. But I want to say a word about the so-called, which has been implicit in our discussion. I just want to bring it out. And the statement is that a stationary black hole, and there are many versions of the so-called no-hair theorem and different kinds of theories with different matter content and different number of dimensions. I'm not going to try to review them all. But a stationary black hole in Einstein-Maxwell theory is characterized or is uniquely characterized by the three parameters M, Q, and J up to diffeomorphisms. So that's saying that so the earliest versions of this were discovered in the 60s, and it was famously called the no-hair theorem by John Wheeler, who said that the solutions of it's surprising that there are no that there's so much uniqueness, that there's so few solutions. So to compare to, say, a star, if you have a star, in some theory with atoms and so on, there are huge number, exponential of Avogadro's number of different solutions corresponding to individual molecules and atoms in different positions with different velocities and so on. And you might wonder, why can't we, for example, why can't we take a black hole and give it dipole charge in Einstein-Maxwell theory? Why couldn't we have, magnetic or electric field lines coming in? And well, you try to do that, you can show that the black hole swallows up the dipole moment, will flow into the black hole, some radiation will come back, and the only stationary solutions are just characterized by mass charge and angular momentum. You can't have any stationary solutions with any kind of higher multipole moment. The only thing that you can have is the spin, and that's certainly far from obvious when you first write down the equations. It's not a trivial thing, but it is a mathematical theorem. However, this up to diffeomorphisms is a little sort of crack in the theorem that you can drive a truck through. And it has been, and I'm just talk about this briefly because it's a little off the subject, but it has been, I think the theorem has been widely misinterpreted. So the first thing about up to diffeomorphisms, if you just think about it for a second, this obviously doesn't mean that the parameters, that there are only 3 parameters. Let me forget about the charge for the moment. That there are only 3 parameters describing or 2 parameters, the mass and the angular momentum, because, for example, the angular momentum could be pointing, up or down or left or right or backwards and forward. And those aren't the same thing. But they are related by diffeomorphisms, right? A global rotation, which is a diffeomorphism, will change the direction that the angular momentum is pointing. Or suppose there isn't even any angular momentum, just a Schwarzschild black hole, we can boost it. That's a diffeomorphism. A boost is a diffeomorphism. And that will change the energy. And certainly we would never want to physically identify 2 things with different energy and momentum. So at the very least, you would want to say, you might think, okay, well, I understand all of that. There are only, there's actually 4 parameters. The energy momentum plus 3, the direction of the angular momentum, plus the charge, that would be a total of 8 parameters. But that turns out not to be right either. If you try to say that carefully, and this was shown in the 60s by Bondi, Metzner, Vanderburg, and Sachs, there is no consistent way. So you might say, okay, I want to think of things which are equivalent under diffeomorphisms except boosts and rotations. But it was shown by Bondi, Vanderburg, Metzner, and Sachs that there is no covariant way, that there's a much bigger infinite dimensional group called the BMS group, which contains rotations and boosts and translations. Also, sorry, I should have said 11 parameters, because a black hole here is not the same physical quantity as a black hole in the science center. They're different. So what was that? That was 4 plus 3 plus 3 plus the charge. That'd be 11 parameters. So it turns out that there is no, and this is a subject for a much longer discussion, but there is no generally covariant way of selecting out 11 special diffeomorphisms and say that only those, 10, and saying that only those 10 map black holes to inequivalent black holes. That runs in conflict with basic principles of general coordinate invariance. Instead, you need this whole infinite dimensional group. And the whole infinite dimensional group, there was a lot of confusion, which was sorted out recently, about how it acts. Well, some aspects of it were sorted out. It's still a work in progress. But in fact, they're an infinite dimensional family of black hole solutions that are obtained by diffeomorphisms of this basic solution. And this is work that Hawking and Perry and I started a couple of years ago. And I think that it will be, how it fits in with the discussion we're having today is, again, still a work in progress. So, well, I'm trying to stay back in 1970, and that was a big zoom up to the present. But so for the current discussion, I'll treat it this way, but it's important to put that caveat in. All right. So one other thing I want to say here is that you can also show that what's sometimes called the zeroth law, that kappa, the surface gravity, is equal to a constant on the horizon. So this is the zeroth law of black hole mechanics. And these laws were written down in the early 70s. And it was noticed at that time that they look an awful lot like the laws of thermodynamics. So let me draw them in parallel here. Let me draw the laws of thermodynamics. So the zeroth law of thermodynamics is often written as the temperature is equal to a constant in thermal equilibrium. The surface gravity being constant on the horizon is a statement about the stationary solutions. So we have so in thermal equilibrium, this is sometimes referred to as the zeroth law of thermodynamics. And then the first law is written as okay, I've written it a different way here. As let me rearrange this one. So the first law of thermodynamics is that the temperature times the change in the entropy is equal to the change in the energy. But that is when you have a system which is labeled only by temperature and energy. In general, we have other kinds of potentials that we might consider. And for example, the one that we see the most often is PdV. But if you have an angular potential, then you would also get a minus omega dj. And if you have an electrostatic potential, if you have an ensemble where you can change the charge and you have an electrostatic potential, you would also get minus phi delta q. And then finally, we have the second law, the famous second law of thermodynamics, that the change in the entropy in any process is always non-negative. Now, when people who were working on this first noticed this, they said, okay, there aren't that many equations you can write down. This is just a coincidence. And they were actually, interestingly, rather adamant that this was just a coincidence, that these laws look similar. But let's just notice that if we take S and we exchange it with any constant alpha times the area, and we take T and exchange it with 1 over alpha times kappa over 8 pi, then then these things turn into one another for any alpha. Now, already at this very early stage, so obviously you know where I'm going. We want these to actually be the same law. But already at this very early stage, quantum mechanics is showing up. And here's why. Because the entropy is dimensionless. And we think of it as the logarithm of the number of, you can introduce units of entropy, but it's naturally thought of as the logarithm in statistical mechanics as the logarithm of the number of microstates, which is just a dimensionless number. And on the other hand, the area has dimensions of length. And in general relativity, so this alpha, length squared, so this alpha better have dimensions of 1 over length squared, and but it has to be some universal quantity. And the only way we can get in gravity, there is nothing with pure Einstein gravity. There is Newton's constant does not have dimensions of length squared. You need to multiply it by h bar to get something dimensionless. And so you have to have an h bar in here. And in fact, we'll see a little later, it's going to be a 1 over h bar. So in order for anything like this to be true, quantum mechanics has to come in. So we thought we were doing classical physics, and all of a sudden, h bar is sneaking in out of the blue. And moreover, Boltzmann didn't need h bar. He was talking about classical systems, and if you look at the entropy of a gas or something, the way that it scales, there's a log of h bar in there, and that just affects the zero of the entropy. So he didn't really need to talk about, quantum mechanics hadn't been discovered. But the entropy of a classical gas doesn't, just has a free gas in a box, just free photons in a box or something. It just has a logarithm of h bar. So, and it's coming in with a 1 over h bar, which is telling you somehow the h bar is very important. It's not somehow a correction. So in thermodynamics, so this is thermodynamics, and I alluded a moment ago to the statistical mechanics description, where we would write the entropy is some function of the energy, whatever. Well, we don't have this. We aren't working in a finite volume ensemble, but we would have some entropy, which is a function of the energy, the angular momentum, and the charge. And we would hope to have to compute this as the logarithm of some number of microstates, and then we would have the usual thermodynamic relations. Where, ds is equal to ds dE plus ds dQ. This is how Boltzmann would think of the first law, ds dQ dQ. plus ds dj, where this is 1 over the temperature. This works out to be 1 over the temperature, the angular potential over the temperature, and this works out to be the angular potential of the system over the temperature. Okay. So this analogy appeared in the equations. And then the next thing happened, or roughly at the same time, Bekenstein, who I think was then a student of Wheeler and also involved in the discussion, started thinking about the rather bizarre thought experiment where there was a way of thinking about black holes at that time. Remember, we only had classical black holes. There's no discussion about quantum black holes. As regions of space-time which were not part of the physical universe. And part of the idea behind cosmic censorship, which we were talking about a few minutes ago, is that we shouldn't be worried about a singularity inside the black hole, because inside the black hole is not part of the universe. We only care what happens outside the black hole. And so it sounded a little weird at the time, but it was a great idea. Bekenstein said, well, wait, if the black hole is not part of the universe, what happens to the second law of thermodynamics? Suppose I have a cup of coffee with some entropy, and I throw it into the black hole. What happens to the second law? And, doesn't that violate the second law? We had entropy in the universe, and the entropy disappeared because we threw it into the black hole. And then he came up, just from this reasoning, with the idea that you would save the second law by saying that the black hole itself has an entropy associated with its area. And that when you throw the cup of coffee in, the total entropy should be the entropy of the black hole, which he put proportional to the area in order to make this work. He realized already that the area was the only possible thing you could associate with a black hole that would make any sense as an entropy, that the area should go up, and that he proposed a generalized second law that would be that, so generalized second law which is that delta S, the ordinary entropy in matter and coffee cups or whatever, plus some constant alpha times the areas of all the black holes in the universe, the change in the areas, should be greater than or equal to 0. And that this would be a generalized second law which would be valid even when the ordinary first law isn't. Really brilliant idea. And he tried really hard to figure out what alpha would be. And he couldn't, he had all kinds of Gedanken experiments that he thought might give him some handle on what, I mean, he was missing some key ingredients, which Hawking put in later, but he had all kinds of Gedanken experiments that he thought would enable him to compute alpha, but there were some things he needed to be thinking about that he wasn't in order to get alpha. But in order for this to be true, I mean, now we know that it is true, and we know what alpha is due to Hawking's work. But just from this reasoning, he also was able to derive some other kinds of bounds, which are now called Bekenstein bounds. And I like to talk about these because it's just so cool how little went into it, how much you got for so little. One is that there must be some universal constant that the entropy per unit mass must be bounded from below by some universal constant of nature, which he again tried to estimate but was never able to compute. Why did that have to be true? Well, if it weren't true, if you could keep the energy fixed and make the entropy arbitrarily large, clearly you could pack enough entropy into your coffee cup so that you would violate the generalized second law for any constant alpha. If there were no bound whatsoever on this, you could violate the second law for any constant alpha. So it must be some universal property of all consistent theories that the entropy per unit energy is bounded from above by something. And then there's another one, that the entropy which can fit inside the entropy which you could stuff, if it's of ordinary matter, not a black hole, which you could stuff inside some region of area A, that must also be bounded. Because if that gets large enough, if that's larger than this alpha times A, then you could take your configuration with the very large energy, collapse the whole thing into a black hole, and again you would violate the second law. Because once you collapse it into a black hole, it's gone from the universe, and that would violate the second law. Now I'm in a little trouble here because my blackboard's midship. Okay, I'll erase this. So now notice we can also write this as S is less than some constant times A. And this entropy that we're associating with a black hole, it's very funny. It's going like an area, so it's going like length squared. So if you have a box of gas at fixed temperature, the entropy is extensive. And it would normally, if you keep the temperature fixed, the entropy would go like L cubed. And indeed, if you want to make a computer, you want to have a bits in it, the amount of bits that you can get, which is the entropy, it's how many chips you can stack in. It scales like the volume. It scales like the volume of the region that you have available to fit the chips into, not the area of the region that you could fit the chips into. So this turns out, this was the first kind of glimpse of what we now call the holographic principle. Let me finish my sentence. This is the first glimpse of what we now call the holographic principle. And the holographic principle, which I can't really state clearly because we don't understand it clearly, but the vague idea is that degrees of freedom in a theory with quantum mechanics and gravity live on the boundary of the region. They're not extensive. They're surface effects. And it's very contrary to our intuition with, this room is full with air molecules. There's one air molecule per, and we could excite that in different ways. So there's 1 degree of freedom per unit volume. That's how we always think about things. But somehow, even this very kind of elementary reasoning already led Bekenstein to the idea that there's something about information storage, that it's an edge effect. It's something that lives on the boundary, lives on, he didn't use the words hologram, but it lives, that's what happens on a hologram. You encode a three-dimensional image on a two-dimensional plate, and that's what the black hole is doing. In other words, if you take the area of a black hole and you put one chip, you don't fill the black hole with chips, you put one chip in every Planck area of the horizon, that will give you an entropy, which a number of possible microstates, which would scale like the area. Yes, Noah. I answered it. Okay. All right. So, of course, finally, one more thing I wanted to say. We know that if we have a gas full of a gas in a box at temperature T, and then we made of one kind of atom. If we have two kinds of atom, then the entropy of that gas is multiplied by, is doubled. And in general, if we have n kinds of atoms, the entropy goes by a factor of n. So in order to have a universal bound on the entropy that you can fit into some region or whatever, there must be some kind of bound on the number of species of particles. And it will be a finite bound, right? I mean, there has to be a number that binds it. So the amount of entropy you can get into your cup of coffee depends on, the number of flavors of coffee beans that you can get at the grocery store. So there is ultimately an upper bound on the variety of coffee beans. So it's very interesting that just with this kind of elementary reasoning, that you can get a constraint on the spectrum of elementary particles. So it's a very powerful, argument in many ways. Any questions? Okay, so I guess a good point to end here. Of course, we know now what alpha is. And Hawking finally calculated alpha. And how did that work? Well, I said a few words about it before. We'll go into great detail in the continuation of this course. But the basic idea is that surface gravity is like an acceleration. And an accelerated observer in flat Minkowski space from some very elementary calculation in free field theory will detect a thermal spectrum of particles. In other words, if you hold a thermometer in your hand and you put your foot on the gas pedal at some, and you're in free field theory, and you put your foot on the gas pedal at some constant pressure, accelerate fixed number of g's, your thermometer will go up to some temperature related to your acceleration. And you read it on your thermometer. You don't have to know about general relativity for this at all. Now, where general relativity comes in is that if we're going to say that if you step on your car accelerator, you read a temperature, you better also read a temperature when you get near the surface of a black hole. Otherwise, you'll violate the equivalence principle. In other words, in quantum field theory, we don't want observers equipped with thermometers to know whether they're in an elevator on the surface of the Earth or an elevator with uniformly accelerating rocket jets in outer space. So Hawking's argument boils down to that, and that is essentially where the temperature comes from. It's proportional to the surface gravity, which is an acceleration, and you have to work out what alpha is, and with some whoa, mistake in my notes here. Anyway, the Hawking temperature is which brings these two sides together is h bar times the surface gravity. H bar, as I mentioned before, is needed just from dimensional analysis over 2 pi. So this closes the circle. Black holes really are thermal objects. They have a temperature. They radiate. And and there's a generalized law of thermodynamics, but which is in which alpha takes this value, and we could just talk about there's a theorem or a generalized second law in which this delta S, where you include both the entropy of the black hole and the entropy of all the matter. Oh, and of course, once we know this, we also know that the entropy so the Hawking temperature is equal to h bar kappa over 2 pi. And once we know that, we can use dsDE as 1 over t to learn that the black hole entropy must be equal to the area over 4 times Newton's constant times h bar. There's a c cubed here. If we don't set the speed of light to 1, I'm reinstating Newton's constant, which I've been setting to 1. And so that then is the entropy of the black hole. Now, in order for this all to make sense, and this will be a lot of what we're discussing next semester, in order for this all to make sense, just as there is this underlying statistical interpretation of the laws of thermodynamics given by Boltzmann in terms of molecules, there had better also be an underlying statistical interpretation of the entropy of a black hole. Otherwise, you run into various kinds of paradoxes, notably the information paradox. And so, the million-dollar question is, where are the black hole? How do we describe the black hole microstates? And that will be another topic we'll discuss at length. It's a problem not fully solved, but one that we'll talk about in the next semester. Questions?
Yeah. So for the bound on the number of fundamental particles, is that just up to the Planck mass, or does that extend the whole way?
Okay, so there are lots of discussions of this, but so you can refine it, and you would get into, it's not up to the, it turns into a bound of how fast the spectrum of particles can grow with energy. So if you're only considering processes involving things with energies way below the Planck mass, then you can't get a bound on particles above the Planck mass.
Does it say anything about whether string theory can be correct? Because it's got the power.
Well, string theory is certainly consistent with all the bounds. A better question is whether string theory is the only theory consistent with all the bounds. Sophia?
Yeah, I think I have a question almost identical to Adam's, but I was just wondering, like, what if our effective theories break down before we reach this bound? Like, do we have any
If our effective theory is what?
break down before we reach the bound of like how many species of particles we can have? Do we have any idea about that? That scale.
Well, this is a statement about microscopic degrees of freedom. So we have to make sure we have a theory which is, right, effective theory, we can't use an effective theory to compute the entropy above the scale where it breaks down. So,
You see my point? So if we're using the effective theory to find this bound on a species of particles, I'm wondering if it would just break down at an energy scale before we reach the saturation.
well, I think you're asking me if there's a context in which this gives, does this rule out any effective theories? Is it, so this is a constraint on quantum theories of gravity. And there might be situations in which you are foiled from getting a constraint because of effects like what you said. Yes, that can happen. But there are situations in which you do get meaningful constraints.
Yeah, or as you said, reversely, we could get a constraint on like, I mean, we could use these constraints to see where it breaks down. If we found more particles that
Right.
tells us about, that would tell us something. Yeah. That's very interesting.
Yeah.
Can you explain again how the second bound translate the generalized second law?
Well, the logic is that if there were no upper bound of any kind on the entropy that you could jam inside a region bounded by a surface of area A, then you could violate the second law. And the way you would do that is, suppose we had a region of area A, and inside that we had some matter that wasn't a black hole, that had an entropy a billion A. Now let's collapse that stuff into a black hole, which would still be smaller. So it would go into a black hole which would have only entropy A, and therefore the entropy would have gone down.
Just by assuming the entropy for black hole is always alpha times.
Yeah. Yeah. Right. That's the assumption, right? He assumed that, so what Bekenstein was doing was he says, let's suppose there's some alpha. He never managed to compute alpha. Hawking computed alpha. But let's suppose there's some alpha, a universal constant alpha. And he had his reasons, which were not fully rigorous, but turned out to be on the right track, for thinking that there should be such an alpha. That's only possible if this bound is satisfied. And then there's been, a really fun. So then, of course, alpha was computed, and then there's a really kind of fun literature where people try to find some Gedanken experiment where they violate the second law. They put matter into long, thin boxes and lower it down to a black hole, and they think they found a violation, and then it turns out they forgot about the radiation pressure of the Hawking radiation, and you put that in, and it rescues the effect, and so on. So it's a highly non-trivial. There have been lots of occasions where people have like, aha, this can't be right because do this experiment, and then you think about it harder, you realize it does work. Of course, there isn't a theorem, right? Because it's a situation which inevitably involves both quantum mechanics and general relativity, and there's lots of uncertainties whenever those are both in the same room. But there's a compelling series of failed efforts to construct a counterexample. Okay, great. See you next year.